Hey everybody, today we're talking solving trig equations, and basically we're going to be looking at something like this here. And so the idea behind solving trig equations is that there is an infinite amount of solutions typically. When you think about like this equation here, right, sine x equals root 3 over 2. Well, technically, if root 3 over 2 is a line right here, right, because as we think about root 3 divided by 2 being a decimal, basically you could pull out a calculator. So let me grab mine here. Let me just tell you what that actually is as a decimal. Square root 3, where's my square root button? Square root 3 divided by 2 is about 0.9, right? So almost all the way up to 1, which makes a lot of sense there. So you can think about, like, if you were to solve this, right, sine x equals root 3 over 2, yeah, and using your cast rule, you could get an exact value of pi over 3 here. Sine pi over 3 is root 3 over 2, right? We can think about our cast rule like that. But basically, right, there's many solutions, and so you can see in the first quadrant, right, in quadrant 1, let's use black here, you would get pi over 3. But then in quadrant 2, right, after you go through pi over 2, which would be right here, right, in quadrant 2, this is in rad, quadrant 2, you'd get, basically, right, you're going to get 2 pi over 3. Rad. But if we're talking about solving these things here, you normally aren't just asked to find it like on its first cycle. Normally they ask you to solve it on a certain interval. Maybe that's because it's like a real life problem because of time or something like that. And so basically, in this question here, they're really asking us to do it for a negative 2 pi to 2 pi. So on top of this and this being a solution, all we would need to do is subtract the period, right? If I take this point here and I subtract the period, subtract 2 pi, we would get negative 5 pi over 3. And if we subtract the period, which is 2 pi again, you'd get this, negative 4 pi over 3. Negative 4 pi over 3 rad. So in fact, there's actually 1, 2, 3, 4 solutions for a question like this, depending on the domain that we're really looking at there. So when you're solving these things that are maybe a little bit more complicated than this, I'm going to give you some ideas when we don't have the graph here. There's a few strategies. One is knowing the cast rule and the unit circle. These are essential. 2 would be making a sketch. 3, or C, I guess, is trig identities. You probably want to think about your tricks using a quadratic equation, like factoring, group factoring, like grouping your terms, rewriting them using an identity, or match the arguments or angles, and I'll kind of explain that one later on. But be mindful of that domain is clearly important. You can see these ones here, we're just looking at it on one cycle from 0 to 2 pi. So let's actually go ahead and try some of these. Well, basically, the first thing you always want to be doing is isolating for the trig term, if you can. And so in this case here, right, when we go cos x equals root 3 over 2, when we divide the 2 across, this is what we're looking at. And we're looking at exactly what angle this would equal. And so typically when I'm solving these things, I'm looking for a positive cos answer, right? So when we're talking about your cast rule, C-A-S-T, we're talking about a triangle or an angle ending up in this quadrant here, or going all the way around and ending up in this quadrant, that terminal angle there. And so if we're thinking about cos, remember that is adjacent over hypotenuse. I know that this is the root 3, 2, and 1 triangle. And if you remember that little special angle in there, that would give you your first value, and we can say x1 as pi over 6. And to figure out what your second value would be, you know that basically, right, as it goes all the way around, this would be 2 pi minus pi over 6, and you'd get 11 pi over 6. Rad. So pretty straightforward in that sense. It is just a period of 2 pi. It's a regular cosine x, and you're solving between 0 and 2 pi. So you only really need to look at one revolution there. Pretty straightforward. Let's check another one here. This one, again, you want to solve for sine x. And so as you go ahead and do that, you're going to get sine x. You'd move the 2 across, so it'd be 2. You'd divide this 2, so it'd be 2. 2 divided by 2. You're going to get sine x equals 1. Now, when you've got something like this, instead of a cast diagram, it might be nice to actually think about your unit circle. And remember, on the unit circle, we know that sine, right, is giving us the y value. So where on this unit circle gives us a y value of 1? Well, remember, if you actually labeled the unit circle, my drawing is terrible, sorry. But the only spot where this gives a y value of 1 is pi over 2, right? This point right here is the point 0, 1. So the only spot between 0 and 2 pi, right, 1 full revolution where we have a y value, sine, right, is y, of 1 is at pi over 2. So our answer, our only answer, is x equals pi over 2 rad. So that would be your only answer for that one. If we had more revolutions, because we were looking at a bigger domain, you'd have more answers there. So in this case, how would you change your answer in the previous question if you were given domain over, negative 2 pi to 2 pi, or even from 0 to pi, or between 2 pi and 4 pi? Well, basically what you'd be doing, right, is you'd be taking this example here, for instance, and if we were looking at part A, between 0 and 2 pi, that's 1 revolution, right? And so if we wanted to go back to the previous revolution, the previous cycle, all we would do is subtract 2 pi from our answers. And so you'd get your third answer, right? We already had 1 and 2. This was between 0 and 2 pi, so we already know that interval. But between negative 2 pi and 0, all you would do is just go we'll go pi over 6 minus 2 pi. And same thing for this one here, right? For your new fourth answer, you would take your 11 pi over 6, and again, minus 2 pi. So when you do that, if you get common denominators here, this is 1 minus 12, so that would be a negative 11 pi over 6. And then your answer here, you would get, 11 pi over 6 minus 12, so it's negative pi over 6. So there you go. You've got those two answers as well as your original ones, and that is just going to give you exactly what you need there. And just to confirm, or just to show you what that might look like, let's actually do this. So cos x equals root 3 over 2. So you can always check using Desmos, and you can go cos x, and then you can just solve by saying y equals square root 3 over 2. We need that to be separate. And you can see here's my answers between 0 and 2 pi, right? So 2 pi would be about here, so negative 2 pi. So there's negative 11 pi over 6, negative pi over 6, pi over 6, and 11 pi over 6. If we were asked to go further, again, all you would do is add 2 pi to get to here, and add 2 pi to get to the next one as well. So it's always just adding the period there. If it wanted it just between 0 and pi, well, obviously you would eliminate the 11 pi over 6. And if it was this one here, you'd eliminate both of them, but just add 2 pi to both your answers to get the next two there. So that's how that would be done. All right, so if you don't have a special angle, like this one, for example, secant x, you still solve and go ahead and you move your 5 over, so this becomes negative 5. You divide your 2, so you get secant x, which we know is the reciprocal of cos. So cos x equals, and we can just flip the negative, so negative 2 over 5 like this. But remember, we need to make sure our calculator's in radian mode because we're going to be using x equals cos inverse of negative 2 over 5. Now be careful, we're looking at this domain right here. So first off, I like to look at my initial singular rotation. And I'm going to be looking at when is cos negative. Well, if we're following our cast rule, right, cos is positive here and here, so it's going to end up in this quadrant and this quadrant. So I draw my little triangles. I know those are my first two angles as we go around, right? We'll call this one x1, this this one x2, but we're also going to be taking one and finding in that negative pi quadrant afterwards. That would be going backwards, but we're going to start with these first two. So let's see, when we use our calculator and do cos inverse, I'm going to make sure my calculator is in radian mode. 1 second, I'm going to pause. All right, there we go. After getting all that set up, you learn that this is 1.98. So thinking about 1.98, let's figure out like which of these two angles did we just solve for. Remember, pi is 3.14, right? So that would have been half a circle, or 180 degrees. So it would have had to been our x1, right? x1 is 1.98. So we can actually even write that in. x1 equals 1.98 rad. Now, one thing I want you to understand here is you need to get this x2. You can do that a couple different ways. You can do pi minus x1, and you can figure out what this little angle in here would be, and then hopefully you can see that, this little angle in here, and then you'd find pi plus that little angle. The other thing you can do, though, is if you just do 2 pi minus what you would have said as x1, right? So x2 is all the way around to here, but minus, because it's symmetrical, 1.98, you'd be able to get that value in there, a second one. So x2 would just be 2 pi minus 1.98. And so for me to calculate that, I'm going to go 2 pi minus 1.98, and we're going to get 4.3 rad. Now, remember, we're looking to go back to negative pi as well. And so obviously, if I was subtracting 2 pi from here, we would go all the way around and end up back here, which would be past negative pi. So we're actually going to be taking our 4.3, right? To get our third x here, we'll be taking 4.3 and subtracting 2 pi to go all the way back. And basically what you'd get here, right, because we're always subtracting the period, and the period of cos is 2 pi, right? This is the period. You'll need to know that later because sometimes the period changes. For example, sine 2x. So yeah, as you do this, right, 4.3 minus 2 pi, you're going to get negative 1.98. Sorry, we're going to go 1.98 rad. If you had tried x4, which would have been 1.98 minus 2 pi, you have not been in this interval here, right? So not good. But yeah, these are your three answers here, 1, 2, and 3. All right. So this one here, sine 2x equals a half. There's a couple interesting ways of solving this, but basically here is the idea. You just kind of want to treat this like it would be like a sine equals 1/2. And so kind of what we do, what this is saying here, is let's let 2x equal theta. So really, now we're going to be solving is sine theta equals 1/2. I know that might sound like you're cheating for a second here, but it's just going to make like the solving of all of this a little bit easier. So when you're doing this now, and again, we are solving it between 0 and 2 pi, so one rotation, what we're going to do is, right, we're going to draw our little cast diagram. I know it's a positive sign, so it's going to be here and here, opposite over hypotenuse, right? This is the 1, 2, root 3 triangle. Basically, I would get my first theta, right, would be pi over 6 rad, and then my second theta, not my x, right, that's not my answer, but my second theta, like in this example, would be pi minus pi over 6, so 5 pi over 6 rad. All right, so at this point, these are not our answers, clearly. I can even pull that up and show you sine 2x equals 1/2. If we do that here, let's change this to sine, and then 2x. And we want to get this to 1/2. I'm also just going to quickly change the step here to be pi over 2, so we can see this a little bit easier on our x-axis for you guys to look at. There's going to be something here, and let's actually, I think I can make this just go between 0 and 2 pi, so that might help people understand what we are looking at here. Notice that there's actually 4 answers, right? because the period of sine 2x is actually pi. And so obviously when we look at the answers here, pi over 12, 5 pi over 12, that is not the first two answers we see. We see pi over 6 and 5 pi over 6. But remember, we initially let 2x equal theta. So now switch back over and say that 2x1 equals pi over 6, and 2x2 equals 5 pi over 6. When that 2 is divided, it's going to be pi over 12, so x1 equals pi over 12 rad, right? 2 times the 6 on the bottom. And this x2 equals 5 pi over 12 rad. Now this is obviously, right, thinking about this period here, this is going around one cycle, but it only has a period of pi. And so we have only actually solved, if thinking about the graph of sine x, right? Ooh, sorry, that got a bit glitchy on me here. Thinking about the graph of sine 2x, it has a period of pi. So we've actually only found, this is 1/2 here, the first two answers. And so we would need to theoretically go all the way up to 2 pi, because that's where our domain is, and we would need to find these two as well. And so all you do is, again, add the domain, right? We know the domain is pi here, so you are just going to add pi to both of those answers. It's not really letting me switch back to black here, but anyways, we'll steal that. So our x3, right, if this is the first x, this is the second x, x3 is just adding pi to pi over 12. So pi plus pi over 12 is going to be 13 pi over 12 rad, and x4 is going to be pi plus 5 pi over 12, which is again 12 plus 5 is 17 pi over 12 rad. So let's confirm with Desmos. You can see that yes, it is 13 pi and 17 pi over 12 rad, which is what we got there. So that's how you solve these particular equations. All right, here's where we are going to be looking at factoring a little bit here. So when you're factoring something like this, I find it easier, you don't have to do this, but I find it easier to let, for just 1 second, cos x equal to like something like a. And so when we see this, this is really 2a squared minus a minus 1 equals 0. And I do this because I see this as easier to factor, and that's really what we're doing here. So when you go ahead and factor this, remember 2 times negative 1, we're looking for what multiplies to negative 2, sorry, what two numbers multiply to negative 2, and add to negative 1. And that is going to be negative 2 times 1 and negative 2 plus 1. So I'm going to get 2a squared minus 2a plus a minus 1 equals 0. Factor by grouping, you're going to get 2a minus 1 plus, sorry, instead of a, plus 1a minus 1. And you get 2a plus 1 a minus 1 equals 0. So at this point, right, I can think of two factors here. I can think of 2a plus 1 equals 0, so solving for that, we get a equals to negative 1/2. And over here, we get a minus 1 equals 0, so a equals 1. Now remember, this is really just cos x, right? Cos x equals negative 1/2, and cos x equals 1. And at this point, we can solve each of those. So there's actually multiple solutions for this. And so if, again, you were to solve these are relatively easy, just like the first ones we had. There's 2 negative quadrants for cos. A over h, that's the 1, 2, root 3 triangle. Remember, this is going to be a little reference angle of pi over 3 in here. So your x1 is pi minus pi over 3, which is 2 pi over 3 rad. And x2, which is the second one there, would be pi plus pi over 3, which is 4 pi over 3 rad. This one here, when you've got something like a solid number, I find it much easier to think about it on the unit circle. And remember, this is when x is 1. So thinking about this, when is the x value 1? When you've got 1, negative 1, negative 1, and 1 for your x and y axis. The only spot when it is truly 1 is over here. But remember, that's a bit tricky because that is the angle of 0, right? So I've got x3. We're going to get 0 rad where it's not moved anywhere, but it's also the same as if you were to go all the way around, end up in the same spot, which would have been 2 pi rad. So there is still 4 locations for that. And again, you could check with Desmos, graph this function, and just see that this will be true, right? This thing will equal 0 at 2 pi over 3, 4 pi over 3, 0, and 2 pi rad. Awesome. All right. Then again, when you're looking at these here, basically something like this is actually a little bit simpler. You just need to go ahead and go tan squared x equals negative 1 over 3. And then basically you need to take the square root because it is easier to solve that way. The only thing I caution you on, when we take the square root of negative, it is no bueno. So that is, yeah, that's not possible. Let's just confirm that. 3 tan squared x equals negative 1. So let's look at that. 3 tan squared x. Yeah, there's no way, right? When you look at this, y equals negative 1, it never touches. So there you go. This one, right, you get equals, my pen just stopped working, 1 second, sorry, I gotta plug it back in. But you can see that as you take the square root there, you would see that it is an error, it doesn't exist. So we are good to go there. Let's change this question because I wanted to show you something with this. I think I meant to have this as a +1. If this was a +1 now, just so we can see, this would be plus or minus the square root of 1 over the square root of 3. This is what I intended it to be, I think, in the end here. And remember, when you take the square root, you get a plus or minus. So you're actually going to get two things. Right? You're going to get tan x equals positive 1 over root 3, and you're going to get tan x equals negative 1 over root 3, just because of the plus or minus aspect. And then for each of those, right, you can use your special triangles to solve for 2 spots. And so thinking about this here, right, let's give ourselves some space. Tan, where is tan negative, right? C-A-S-T, I guess this is positive. Tan is positive here and here. So if you're thinking about opposite over adjacent, what angle is that? Well, that would be our first one. X1 is pi over 6 rad. And then the second one, right, as you go around to the second thing there, would be pi plus pi over 6, which is 7 pi over 6. And then this one here, these are basically the opposite, right? If we were to draw our CAS diagram, instead of being in the 2 positive quadrants, it is in the 2 negative quadrants. But you're going to get the same thing, right? Opposite over adjacent here. It's still going to be pi over 6, but now you're going to get your third value is pi minus pi over 6. So that'd be 5 pi over 6 rad. I should be writing rad on all these, sorry. Rad. And then the last one would be 2 pi minus pi over 6, right? Which is 11 pi over 6. And pretend I wrote rad there, I ran out of room. All right. Just a couple more here that I feel like we should look at. So we'll start with this one here. I don't think we'll do example 5, just you guys could do that. It's not too hard, it's just a word problem. These are the ones that are the real meat and potatoes here. But yeah, let's look at this one here. So obviously this, you try this, it's ugly, it's not the same thing. We can't really factor that. And so hopefully you remember your identities here. I want to change all of these to the same thing, and that's kind of the strategy here. So really what you want to be doing is, instead of cos squared x, remember the Pythagorean identity is sine squared plus cos squared equals 1. So really cos squared can be written as 1 minus sine squared x. And when you do this now, when you simplify everything, let's bring it all to one side, right? So we're going to get, let's write it all out so I'm not going to lose any numbers here. So this would be minus 12 sine squared x, and then we bring the sine x over, so minus sine x. Let's go 0 equals, we're going to put our sine squares in the front, so negative 12 sine squared x, and then we're going to get minus sine x, and then we're going to get negative 6 plus 12 is plus 6. Yes, why did that take me so long? All right, good. Let's just multiply everything by negative 1, just because I don't like the negatives in the front. So 12 sine squared x minus sine x plus 6. Now, is this factorable? To not spend too much time humming and hawing, let me just see the... All right, as I looked it over, it is not, but the way that you'd figure that out, right, is 12a squared, so letting sine x equal a, 12a squared minus a plus 6, and then basically, right, you just need negative b over 2a, so negative 1 over, we need the b squared minus 4ac, so negative 1 squared minus 4, 12 times 6, and is this positive or negative to figure out what our x-intercepts are, or how many of them there would be, right? That's 1 minus a really big number, so it's negative, so this does not exist. So there's no solutions for this one here as well. So there you go, that's probably enough talk for today. There is a practice sheet. If you need to go back and pause at any point, I'll ask questions, that's great. We will kind of recap this on Monday as well. So thanks so much for listening.